let's say we have a neutral conducting plate here and a neutral conducting plate here. Now, we grab a piece of positive charge from this plate, and we're going to physically move it over to the other plate. So then this one would have a positive net charge, leaving this one with a slightly negative charge as well. The next time we grab a piece of charge from this side and we move it over to the other side, we will have an electric field that we have to push that charged particle through, that positive charge through, and in doing so, we have increased the energy of that positive charge by separating it from the right plate. If we continue to do this, so grab another one and move it over, then we'll have a positive charge here and a negative charge that was left there. Now, this gives us a separation of charge. And every time we were doing work on a little bit of charge to move it from one side to the other. So in the end, we'll have charged plates. So the work done by the external force, that is you scooping the charge from one plate to the other, will be equal to the change in energy of the system. So all the little tiny work that you did externally will be causing a change, creating a change in the electric potential between the two plates, meaning that every little bit of charge that we moved from one plate to the other is gaining energy. That energy is equal to the work done by the external force. This would mean that graphically, as our potential difference is changing, the charge is also changing. And as we added from the right side to the left side, we were increasing the charge on the plate. So this Q will represent the total charge on the left plate. This relationship is linear. And so Q will equal some slope value times delta V. The slope is referred to as the capacitance. So that means that Q is equal to C delta V. Or in our case up here, our delta V would be equivalent to the little bit of charge at any time, because we're looking at a small change, a little bit of charge divided by the capacitance. So the little bit of work done by the external force is equal to the change in potential difference times the little bit of charge that is transferred. Using the relationship earlier, we can write our change in electric potential as being the little bit of charge that is collected divided by the capacitance. So then we would have that dW, the derivative of the work function, would be equal to Q, charge, over C, the capacitance, times dQ. Integrating both sides, dW, integral of Q over C dQ, with the limits of 0 to W for all the work done, total work, and 0 charge to the net total positive charge on one of the plates, we would get that the work is equal to Q squared over 2C. Graphically, if we look at the result of our work being the product of our potential difference and charge. So if this is Q versus our delta V, and we had the data showing that the relationship was linear and positive, then the area under that curve multiplying Q times delta V gives us the energy stored, which would be equal to the work done. So that could also be written as 1/2 Q delta V. And similarly, since Q would be equal to delta V times C, we could write this as 1/2 C delta V squared. The slope of the charge versus potential difference graph is equal to our capacitance. That is the capacity of our arrangement to hold charge and thus energy.